So last time we started to discuss quantization itself. So the BV quantization procedure can be split in the following steps. So first we start with classical action. So this is classical action, just action of our system. We identify gauge generators. If present, we identify identities and in principle higher structures. And all this gives us proper master action. S, which satisfies classical master equation. So this is the first step. So S knows everything. We think about our theory. It contains all information, action, gauge generators, everything, and a master equation ensures that all these structures are compatible. So it ensures gauge invariance. Okay, then we look for quantum corrections. So we look for, sometimes it's called quantum action. Which is W and which is S plus possible corrections, etc. These corrections take into account, I'll comment on this, take into account the fact that in general, the measure in the path integral is not invariant under BRST transformation. And to cure this, one adds these corrections W. Let me remind you, by the way, I'm afraid I made a typo or mistake. Well, typo because it's not conscious. So if you expand quantum master equation, which look like this, where delta is a delta operator, which we discussed last time, to first order in H bar, it gives, so at zeroth order, it gives us SS equals 0, but at first order, it gives us SW1 equal to IHS, right? This is zeroth order, and this is first order. So you see that if, oh, sorry, here is delta. If delta on S is 0, then there is no need for W1, right? W1 equals 0 would perfectly solve the equation. So the corrections are not needed in case if delta S is 0. But what is delta S? So we have this BRST differential S, which is a bracket with S. And what it looks like TS over D phi D over D phi star plus ds over d phi star d over d phi, right? And let's take divergence. So this is a vector field, right? This is a vector field. What is divergence of this vector field? It's precisely, so if we have a vector field which reads like this, it's say V equals to V I T O D Z I in some coordinates Z, then divergence is precisely d over dz I of vi. Then if we compute it, so and here the derivatives are acting from the left. So if we compute it, we see the divergence of S is precisely proportional to delta of S. So so this delta operator measures the divergence of the Hamiltonian vector field with Hamiltonian S. Of course, to speak about divergence, we need to fix a particular volume form. Otherwise, we don't have a concept of divergence, right? But now we don't discuss formulation in general coordinates. So we just assume that we work in a given Darboux coordinate system of certain choice of fields and antifields. And in this coordinate system, the divergence of Beresty differential small s is precisely delta of s. So if Beresty differential preserves the volume form, which means the divergence is 0, there is no need for this W1, W2, and further corrections. And classical master action solves quantum master equation. But in general, it is not so. Another comment which is appropriate here is that all these discussions of measure, etc., they are very formal because the space is infinite dimensional and there are many issues, including the issue of how well this delta operator is defined. But suppose if we ignore all of them, the philosophy is like this. So delta operator has to do with the measure in the path integral, and quantum master equation controls gauge invariance and its compatibility with measure, so that the Beresty transformation, the quantum Beresty transformation, is already compatible with the measure and really leads to a gauge invariant path integral. Okay, very good. So one way or another, suppose we obtain this quantum action. This is the main ingredient for the path integral, and then we can consider quantum overage of an observable f, which is just a path integral over phi of the exponential I over h bar w f, and all this is gauge fixed, which means that one needs to replace antifields with derivatives of the gauge fermion. This is the prescription. Again, we don't get into any subtleties, and we treat path integrals formally as if they were usual integrals. And provided that W satisfies quantum master equation, and S W minus SF minus IH bar delta F is 0, which means that F is a quantum observable, so it's annihilated by quantum Beresty differential. F is psi independent. Of course, psi independent means that it doesn't depend on a small infinitesimal changes of the gauge fermion psi dependent. If we pick a completely different gauge, we can get something different. But this can belong to different topological classes, etc. This is already beyond our control. But what we want, at least we want to make sure that if we slightly change our gauge fixing surface, which is this surface, then we don't get any any changes in our physical observables, which are these quantum averages. Okay, and of course another condition is that psi should remove the degeneracy of our functional, which means that it should be a good, it should contain a good gauge condition. Okay, fine. So this more or less is a very minimal version of BV quantization prescription. As you can see, it is quite universal. It doesn't depend on which particular theory you are considering. You represent a given gauge theory in terms of as a universal BV theory, for which already the quantization prescription is one and the same. All gauges are controlled by the choice of this gauge fermion psi, while all compatibility, all gauge invariance, all properties are controlled by quantum master equation and the condition imposed on observables, on quantum observables, that they are annihilated by quantum Beresty differential. Okay, good. To illustrate the usefulness of this description of quantum theory, let us see how word identities can be compactly found in terms of this formalism. Word identities associated to Beresty symmetry, which are very important, for instance, in renormalization, because this is a condition that you have control during renormalization. Okay, for this there is an important technical trick. The trick is that instead of setting antifields to their gauge fixed values, it's much better to keep them as parameters. So the idea is to consider W psi, which is just W of fields and shifted antifields. So we just make the following change. And we keep the dependence on antifields. If we now substitute, and the same we do for observable if we insert one. If we now we can, for instance, consider the generating functional of green functions, so which is Z psi, which we can define. Now it's going to be a function of sources Ji and antifields I star I, and which by definition is just a path integral of the exponential together with the source term, right? So if we evaluate this Z psi and set phi star to 0, we get a usual definition of generating functional, right? Because our W psi becomes just W evaluated at our gauge condition. But so phi star are just parameters which we can, because we don't integrate over them, we can keep dependence on them, and this turns out to be quite useful. So it's better to work with this object because this extra dependence can be useful. Then, in terms of this generating functional of Green's function, we can we can find identities which are precisely the word identities. The trick to obtain them in a nice form is as follows. So you just consider the identity. So 0 equals to d phi, and then let's write delta h bar psi plus. For instance, like this. This is 0, right? Because if we integrate something which is delta exact, we get 0 because it's like a total derivative in the field space. But at the same time, we know that this expression, the integrand, what we have under the integral sign, should contain, is proportional to quantum master equation, right? But not for W psi, but for W psi plus J phi. So let me write this. So this equals to, again, integral d phi. Here we get master equation on this, but I don't write the master, because among the terms of this big master equation, I'm going to find delta on W psi, also W psi with W psi, which is a master equation satisfied by W. I drop these terms. By the way, we need to see why the W psi satisfies master equation. But we will do it after. So suppose it is correct. So the only term, and also delta acting on this term gives 0 because there is no anti-field dependence. So J are sources external, they phi and phi star independent. So there is no phi star dependence, so delta operator vanishes this term. So the only contribution we get is an anti-bracket between W psi and Ji phi I, and the same exponential. Same. So the following term. But now we observe that that bracket with Ji phi I is just Ji d over d phi star. But so it can be taken outside the integral because it differentiates with respect to phi star, which is just a parameter. We don't integrate over them. So we write all this, all this is equivalent to Ji d over d phi star I, acting on just the integral of the exponential of W psi plus J phi, but this is Z by definition. So here we get Z psi of J and phi star. How can I remove it? Does it work? Yeah, okay, better. Okay, so and these are precisely the word identities, because you see we get relations between, we get equations on Z psi. Of course, this Z psi is extended by phi star, but we can always evaluate this and then set phi star to 0 or consider different powers in phi star, and we get certain equations Z psi, but because Z psi is a generating function of Green's functions, it contains relations for the underlying Green functions, which has to do with gauge invariance of our theories, with more precisely with the Beresty invariance of our quantum theory, which in turn it originates from a gauge invariance of the initial theory. So one comment which I one remark which I forget to explain is that this W psi, what we used is a W psi satisfies quantum master equation. How can we check it? In fact, it's the easy way to check it is to observe that W psi is nothing but exponential of the following vector field, bracket with psi acting on W, right? Because psi depends only on fields, so this is precisely exponential of d psi over d phi d over d phi acting on W, and this is of course nothing but W of phi star. This is precisely W of phi and phi star plus d psi over d phi, right? That's a simple computation. And then it's again a simple computation to check that delta commutes with this operator. The delta psi f equals to psi delta f. So the operator delta and the Hamiltonian vector field with Hamiltonian psi commute. This is easy to check because delta satisfies Jacobi for anti-bracket. Delta acting on a bracket of fg is just delta f g plus minus 1 to power, if I remember correctly, f plus 1, f delta g. And this is an exercise to check it. Exercise check. Okay, so we completed our derivation. So let me repeat that our word identities in this formalism look like this. So it is just ji d over d phi star I for that psi equals 0. So quite a compact and universal form. There is another formulation of word identities of gauge theory, which has a name, and it has a special name, and because it's very important, of Zinn-Justin equation, which is something like master equation for effective action. So let's derive it. It's an equivalent rewriting of these word identities. So the idea is to introduce the effective action gamma, which is a logarithm of z psi minus j I phi bar I, where we introduced new variables, phi bar I as d logarithm z over dji. So what I'm doing now is just a Legendre transform. So think of z psi as a Lagrangian, and dependence on antifields is now, so antifields are like coordinates, and sources j are like velocities. So we introduce momenta, which are phi bar, which are derivatives of our Lagrangian with respect to sources, and then do the Legendre transform. So we introduce just the sign is opposite for standard conventions, and do the Legendre transform. So we take this log of z term minus j phi bar and then express it as a function of phi bar and phi star. So instead of j, we change coordinates. So this is considered as a, so this relation defines a coordinate change. Of course, one assumes that it is invertible. Coordinate change from j to phi bar. And suppose that this transformation is invertible. Then we express gamma as a function of, strictly speaking, functional, of course, gamma as gamma of phi bar and phi star. So phi star dependence, we did nothing with it. It is just like a parameter. But for j dependence, we made a Legendre transform, and now it's a function of phi bar rather than j. So
is it like an effective action for this?
Pardon?
Is this like an effective action for this?
Yeah, it is effective action, or one particle generating function of one particle reducible diagrams or something like this. Yeah, this is effective. Let's write it here. It's effective action. It's effective action. In field theory, this gamma is already, in usual field theory, is not a local action. It's a quantum object, and it contains non-local terms which encode correlation functions. Effective action. Okay, and now we do just simple computation. We compute d gamma over d phi star is let's compute this. Phi star enters only through, so this is d log z psi over d phi star I. So this is one thing. And this is a bit more involved, but still simple. D gamma over d phi bar, let's compute it, is what? Let me remind you that what gamma is. So it's d over d phi bar of log z psi minus ji phi bar I. Okay. So so this z psi it now is a function of phi star and phi bar, but phi bar is in turn a function of so let me write it like this. It's d logarithm z psi over d j, and then dj over d phi bar, and then minus d over d phi bar gives me the second term. There are two contributions. One is when j is itself, because we changed variables, is a function of phi star and phi bar. So we get here dj over d phi bar times phi bar. I think this is correctly here. And then there is a second term, which is just ji, right? But then you see that, in fact, phi bar is by definition the derivative of log of z psi over dj. So the first two terms cancel, and we get minus ji, of course, expressed in terms of phi and phi star and phi bar, right? Okay, and so we can now we have the following observation, that if we write d gamma, I'm not very careful with sign factors. It can be a good exercise to make them right. Otherwise, if I do everything right here, it will take a bit longer, and we don't have much time. So d gamma over d phi star I, d gamma over d phi bar I is of course proportional. Again, let me be sloppy with coefficients. Is proportional to what? We get ji, right? And we get from here, we get this derivative, which in turn is proportional to just dz psi over d phi star I. And these are the word identities. And if we now denote by the same symbol, anti-bracket, the anti-bracket in the sector of phi bar and phi star minus exchanged, then we can write it as this relation, because this is 0, because this is word identities. We can write this relation as gamma gamma equals 0, and this is precisely this Zinn-Justin equation. It's another way, and a very convenient way, because it again has a form of master equation, and all homological technique can be applied. It's again it's a useful reformulation of word identities, which has the form of master equation. And in fact, the classical part, one can prove that classical part of gamma is just the classical action. So let's say that gamma is something like S plus H bar or something, and S is a classical action. One can see that, again, one can analyze this equation in terms of the classical BRST differential, which is a bracket with S. If you do expansion in H bar, which gives a powerful technique, and this is precisely the technique which is mostly used in, and these equations are mostly used in the context of renormalization of gauge theories. Okay, we don't get to this direction too far, but what we discuss now is equivalence, and in fact it's a kind of derivation of BV quantization, but I call it equivalence between BV and BFV. But because BFV can be phrased in terms of operators, where it's a kind of natural extension of quantum mechanics, we can derive BFV quantization from first principles. But it turns out that BV can be derived from BFV, and in this sense, it gives the first principle derivation of BV formalism. Why are we actually allowed to quantize our theories by these rules, which we justified a little bit? We just considered the question of how can we extract something gauge invariant out of BV formulation, and argued that we need to integrate over a surface parameterized by gauge fermion, which encodes gauge conditions, and there should be gauge independence, etc. But still, it's not really a first principle. It's not really a first principle derivation of BV. but this sorry, just one moment. But if we can derive BV out of operatorial quantization, then we are on more solid ground. Okay, so let's try to do it. For this, let's get back to first-class constraint systems, because as you can see, they play extremely important role in our understanding of what's going on, because they are like prototypical examples of gauge systems. So suppose we have a first-class constraint system with a phase space M0, and we have symplectic structure, we have Hamiltonian, we have constraints T alpha. And you remember that equations of motion read like this: z dot a equal to z a with h naught plus z a with t alpha lambda alpha, and t alpha equals 0. And lambda alpha are our Lagrange multipliers. And if you remember, it's obvious that solution to this equation exists for any lambda, for any functions lambda. You can also assume that lambda depend not only on time, but also on phase space variables. And picking different lambdas, we access different solutions, which are gauge equivalent. So if we start with a certain initial data at time equals 0, and find a solution, find different solutions satisfying this initial data, but corresponding to different functions lambdas, all these solutions are going to be gauge equivalent. They describe one and the same physical solution, right? But these equations can be written differently. We can, instead of h naught, we can introduce h prime, which is h naught plus lambda alpha t alpha. And now we think of lambda as some given function on phase space and time. And of course, these equations are just, this first equation is just rewritten as z dot a equal to z a with h naught prime, right? Because this term in the Hamiltonian reproduce this term plus additional one, but additional one is proportional to constraints, so it changes anything, because we have a second equation telling us that constraint should be satisfied on shell, right? So this means that we can think of, we can interpret gauge transformation differently. We can forget about Lagrange multipliers and think of gauge transformation think of a change of gauge as a change in Hamiltonian. If we add to Hamiltonian terms proportional to constraints with whatever coefficients, we go from one dynamics to a gauge, we describe a gauge equivalent dynamics. Is this point clear? Hello, can you hear me?
More or less, yes, it's clear.
Okay, good. So let me repeat. So it's just a point of view. So before, we were thinking of lambdas as of additional variables which are unconstrained by our equations of motion, so we can set them to any functions of time. And this arbitrariness corresponds to gauge arbitrariness in our solutions. Now we can change a point of view a little bit. We can say that instead, let's think of lambda as just coefficients, some some additional functions and put them inside Hamiltonian together with constraints, to add this term. Then the dynamics determined by this primed Hamiltonian, let me also call it H not prime, this dynamics is going to be equivalent, but this is going to be like dynamics in a different gauge. So before we changed, the change of gauge was the choice of gauge was the choice of lambda. Now the choice of gauge is the choice of Hamiltonian, but of course the choice among the equivalence class, because you remember that two Hamiltonians describe equivalent dynamics if they coincide on the constraint surface, which exactly means that they differ by a term like this. Okay, but once we adopt this point of view, for us, equations now have there is no ambiguity, because ambiguity is hidden in Hamiltonian. So we can perfectly formulate a path integral for our Hamiltonian system, because we have an action, and this action is non-degenerate because it's a usual first-order Hamiltonian action. It doesn't have gauge freedom because this gauge freedom is hidden in the choice of Hamiltonian. You see, let me comment a bit more that when we analyze these dynamics, suppose we start with a Lagrangian and we pass to Hamiltonian formalism, then we don't get a Hamiltonian. We get a representative of equivalence class, and it's a matter of taste which to pick. And this also reflects gauge symmetry in a way, because Hamiltonian is not fixed. It's fixed only up to addition of terms proportional to constraints. And this is another manifestation of gauge symmetry. But still, once Hamiltonian is fixed, we have a well-defined dynamics. Our equations of motion have unique solution for a fixed initial data. So we can quantize our system in a standard way. And we can do it in path integral formalism, because it is known that path integral formalism is just an equivalent rewriting of usual canonical quantization rules, right? So let's do it immediately in BFV, because we can also add ghost variables, and we can pass to BFV formulation. So we can write for instance, we are interested in average of an observable f, which is Beresty invariant, and we can write it in path integral formalism like dz exponential of I over h bar, our Hamiltonian action, z sigma a z dot a, where z variables now include phase space variables and ghosts, minus h, which is now a Beresty invariant Hamiltonian extension of our h naught. And we know that Hamiltonian Beresty invariant Hamiltonian is defined up to addition of a trivial term, which is exactly the same arbitrariness, but now in BFV formalism, which is can be written like omega with k for some function k, and here we put f. So first of all, we want omega f to be 0 for it to be observable, and also we want Gauss degree of our k to be -1, so that Gauss degree is preserved. In minimal setup, k should have a form of, if it's a reducible, minimal formulation of an irreducible first-class constraint systems, and the only object of degree -1 is the one proportional to Gauss momenta. So it's something like this, right? But even, just a moment. Should call it lambda, right? So if I pick such a k, then I know that omega with k is precisely lambda alpha t alpha plus Gauss terms. So this is exactly the same. So in Dirac formalism, the ambiguity in Hamiltonian is described by adding terms of the following form, but in BFV formalism, the same is done by adding terms of this form. Right, and different. So what is written here is just a generic Hamiltonian. It's a particular Hamiltonian plus generic trivial Hamiltonian, which is Beres-T exact, which is a Poisson bracket of Beres-T charge omega with a certain function k of degree -1. So it's same story. Okay, and what does gauge independence mean now? This path integral is perfectly defined because we just have a usual first order action. There is no gauge invariance. We can just do usual path integral like in textbooks. We don't need to gauge fix anything. But where the gauge invariance is hidden, the gauge invariance is now hidden in k, because change of gauge is a change of k. Because if we take different k, we go from one Hamiltonian to another Hamiltonian. Our dynamics changes in an equivalent way. It doesn't classically, it doesn't affect observables, but now we want it not to affect quantum observables, which means quantum averages, right? And this is in fact true, so that this action, this object doesn't depend on infinitesimal variations of k. And this is a well-known statement, which is known under the name of theorem of Fradkin and Vilkovisskiy. Fradkin-Vilkovisskiy, which tells that our f is unchanged under infinitesimal variation of k. Okay, so let's see how it can be proved, because it's a kind of a standard and very instructive proof of gauge independence, which usually happens. There are many statements like this, but this is historically first and maybe most important. But all these statements are proved more or less by the same argument, which is an argument of changing variables and showing that the change in k can be somehow absorbed by a change of variables. Okay, so what we do the following change of variables. We do delta z a equals to z a with omega. So it's like a canonical transformation generated by omega times epsilon, where epsilon is has the following form. It's a functional, it's not a function. So it's a change of variables on, strictly speaking, on the space of field histories, not on the phase space. And epsilon is integral over dt of small epsilon of z of tt. So it's a local functional like this. So what happens if we perform such a change of variables? First of all, because omega h equals 0 and also omega f equals 0, and the same, of course, for the last term, this one, which is also BRST exact, BRST exact and BRST closed. So this term, and this term, they do not change under such a transformation, just because it is generated by omega. Because, for instance, transform delta of H is going to be dH over dZA, ZA with omega, and then epsilon, and this is, of course, H with omega epsilon, which is 0. Same for the other terms. Then there is a kinetic term, which is here. And this kinetic term changes by total derivative only, right? This is a standard, it's like in mechanics. So if we want to see, for instance, well, we can even do it explicitly if you want. If so we have this sigma A, which is a symplectic potential, which is a function of Z, well, in general time as well. Here we have Z dot A. So what is the change of such a term? It's something like this, right? So you get epsilon Z B omega dB sigma A Z dot A, right? Plus, but in fact minus, because what I'm going to do, I don't care about total derivatives. So I can move total derivative on sigma and then just vary Z. So I get epsilon Z A omega, and then I get dot on sigma, which gives me Z dot B dB sigma A, right? And all this combines into, I'm not careful with signs, so it's an exercise to make sure that everything is in order. All this combines into Z dot A, omega AB symplectic structure. Z B capital omega, then epsilon. And this is, of course, nothing but omega dot epsilon. But epsilon is time independent because it's an integral over time. So it is the same as omega epsilon with dot, total derivative. And we assume that it does not contribute. So we see that our all terms in our expression are invariant. So this is invariant, this is invariant, this is invariant, and this is invariant. But when we change variables in the integral, we also need to write down the change of measure, right? The Jacobian of the transformation. This is infinitesimal transformation. So the Jacobian is just, so what is, we consider infinitesimal transformation Z to Z plus Z omega epsilon, right? And we consider epsilon is infinitesimal. So, and what we need, we should even write it like this, because strictly speaking, it's an equal time Poisson bracket, and we really change, this is a change of variables on infinite dimensional space of field histories. So what is a Jacobian? It's just a divergence of this, right? And but divergence in functional sense. So it's an integral dt d over dza of t, right? Of this object. But let me rewrite it in terms of matrix of Poisson bracket immediately. So this is going to be omega AB. And suppose we are in Darboux coordinates, so it's a constant, simplex Poisson bracket, Poisson tensor, and then d omega over dz b, right? And all this at moment of time t times epsilon. So this is, yeah, this, right? Okay. So what we see, so there are two terms. So derivative with respect to z, omega is constant by our assumption. First, it hits this term, and second, this term. When it hits this term, it produces just, because omega is local, it is just second derivative of omega with respect to za and zb times, in fact, there is a singularity there. It's delta of 0 because it's a functional derivative, but it's anyway 0 because omega ab is antisymmetric and second derivatives are symmetric. So this term is cancelled. This is obvious because if epsilon were constant, then what we wrote would be just a canonical transformation, which doesn't change the natural measure on a symplectic manifold, which is a Liouville measure, right? We do Liouville volume form. So the only non-trivial contribution to the divergence comes from epsilon, from derivative of epsilon. And indeed, it's only second term which contributes, which is just integral over dt of what? Of so we have here z a omega d epsilon over dz a of t. But now we remember that our epsilon is a local functional of the following form. So with some function epsilon small, this is a small epsilon in contrast to a big one, and that is why here we just get integral dt of what? Of omega with small epsilon, right? Because d big epsilon over dz, it's a variational derivative, strictly speaking, dz a of t equals what? It equals just d epsilon over d small epsilon, because it removes the integral and you keep just dz a of t, right? And like this. Very good. Yeah, let me do it more carefully. So our big epsilon is integral over dt of small epsilon of z of t and t, right? What we need to compute is variational derivative of big epsilon over d z convention a dz a of t, right? When we take variational derivative of a ultralocal function like this, what happens? The integral is gone. Well, you should think even of t prime, but here is an integration variable, and this is another t. So the integral is gone, and you just get d epsilon over dz a evaluated at t, right? So you substitute it back, and you get what is written here. But so this term, integral dt of a bracket of omega with epsilon, is precisely the term of this structure, right? So it can be absorbed because it's infinitesimal. We can put it in the exponential. It can be absorbed by a change of k. In other words, or other way around, if we change k infinitesimally, we get an additional term, but this term can be absorbed by a divergence of an infinitesimal, of Jacobian term of an infinitesimal change of variables. So all in all, we proved that this expression is independent under small variations of k. And this is the statement of Fradkin-Vilkovisskiy theorem, that this f average is unchanged under small variation of this k. Of course, k is also called gauge fixing fermion because it plays exactly the same role as the gauge fixing fermion in Batalin-Vilkovisskiy formalism, because it takes us from the choice of k, the choice of gauge, because now choice of k effectively changes Hamiltonian, and change of Hamiltonian changes dynamics. And this change of dynamics is precisely the gauge transformation. Okay, now we can indeed relate it to BV. So let me remind you that if you have a BFV system, we can write this. So if you have a BFV system, so which is m omega h, right? So this is BFV system. Then we can find a BV description of the underlying BFV Hamiltonian action, and this is BV action, which has the following structure. We discussed this thoroughly. It's a BV action like this. It satisfies master equation, and it gives it's just a BV action for extended Hamiltonian action. For instance, among these Z star A, somewhere there are Lagrange multipliers. Okay, but now let's consider it as a genuine BV action. Then our BV prescription tells us how to write down path integral, and the important step is to pick a gauge fixing fermion, right? So we pick a gauge fixing fermion, which must be a function of z of Gauss degree -1, right? So we pick z, we pick psi, gauge fixing fermion. And we take it of a special structure. We take it to be psi, to be integral over dt of k of z, right? And let's now see what happens. So our z star a of t must be d psi over dz a of t, and is going to be precisely dk over dz a of t, right? So we substituted back here, right? Because that's the only term which contains antifields. And what we get precisely, let me try to write it here. So this SBV, already gauge fixed, looks like this. It's integral dt. I don't write first terms because they unchanged. Then I substitute z star with dk over dz. So dk over dz times bracket of z with omega is just a bracket of k with omega. Right? So this is exactly the gauge fixed, where it is. Yeah, this action, right? Sigma A z dot A minus H minus omega K. So we recovered our BV action, our BFV action starting from a special gauge in BV. But as we proved, nothing depends on gauge. So if it is correct for one gauge, it's going to be correct for another gauge, up to, of course, all the subtleties about global geometry, Grigoriev-Kupis, etc., which anyway we can discuss. So for infinitesimal, within one class of gauges, for an infinitesimal deformation of gauge, it is okay. So nothing depends on it. So what happened? So it happened that we succeeded to make sure that if we systematically apply Hamiltonian formalism, we could derive the same result as we arrived at starting from BV. So in some sense, it is a proof of equivalence of BV formulation and BFV formulation, of course, for a very special class of systems, which are first-class constraint systems. But then we need to remember that relation between Hamiltonian formalism and Lagrangian formalism is governed by elimination of auxiliary fields. And in BV formalism, these are so-called, what we discussed last time, generalized auxiliary fields. So for instance, this BV action can be, so we have a BV action for a first class constraint system. So what we can check, and this is a good exercise, I'll formulate it later as an exercise. What we can check on examples, at least, that we can, if the underlying action is equivalent to usual second order action, then this BV, via elimination of auxiliary fields, then this BV action can be also rewritten, can be also equivalently reformulated as a BV action for the second order action. Let me illustrate it, because otherwise I'm afraid it's difficult to understand it like this. So let's consider a simple example. For instance, we have a just Hamiltonian system to begin with. So we have Pi Q dot I minus H, this action. Suppose we don't have constraints, right? Then we know perfectly that under standard conditions, Pi are auxiliary fields. Right? Why? Because if we take a variation, what we get Q dot I minus dH over d Pi equals 0, right? And this is just a inverse Legendre transform. So under standard conditions, it follows that Pi is, so these equations are equivalent to Pi equal to some functions Pi of Q and P, Q and Q dot, right? So it means that P is auxiliary field. We substitute it back, and we get our second order action. So so S of Q is of course nothing but integral dt, this p of q dot times q dot minus h expressed in terms of q dot, q and q dot, right? Okay, another bracket. So the passage from Hamiltonian formalism to Lagrangian formalism is simple, right? We just eliminate momenta. We can do the same at the level of path integral. We can just integrate over momenta, and because for them equations are algebraic up to a factor, we just it's equivalent. This integration amounts just to setting them to their classical values. Because they're auxiliary fields, there is no real path integral in this sector. The same can be done for constraint systems, right? Again, example. For instance, our beloved example of relativistic particle. So let's have again p mu x dot mu minus Lagrange multiplier times p squared plus m squared, right? You know that you can, again, lambda must be non-vanishing, let's say positive for definiteness. Again, it's clear that p is auxiliary, and its elimination gives us second order action of the form x dot, maybe half here, x dot squared over I'm not sure with coefficients, but the idea is like this, right? Minus, yeah, half. Yeah, I think it is correct like this. Yes, so again, the story is the same. So even if we are dealing with a gauge system, in a Hamiltonian formalism, we can still get back to second order usual Lagrangian action by elimination of momenta, or integrating over momenta if you prefer the language of path integral. So you can do exactly the same at the level of BV. So when you have this BV action, you eliminate momenta together with their associated antifields to get the BV action, and we know that elimination of generalized auxiliary fields produces again a BV action satisfying BV master equation for the second order formulation. Conceptually it's simple, but I think that the only way to get acquainted with this and to understand is to do it as an exercise. So I suggest show that BV for, let's say two, there will be two exercises. One for relativistic particle. So say Lagrangian equal to p x dot this one gives and second example, let's consider Maxwell. but in first order formalism, sorry. What I want is first order formalism, which is what? Which is Lagrangian density is I d I right minus I minus 1 over 4 Fij, right? It's just Hamiltonian action for Maxwell. So let's say Hamiltonian Lagrangian action for Maxwell. Okay, so that in these two examples, to show that BV for them, which are obtained just from BFV by the standard trick. So what I mean is this one, right? So we obtain, if we have Hamiltonian symplectic structure and omega, we just write down BV immediately, introducing antifields like this. So we know the answer. So this BV in these two examples. So the exercise is to show that, for instance, in any of these examples, this BV for Hamiltonian action gives BV for second order action. Better formulation, because action doesn't depend formulation via elimination of auxiliary fields, generalized auxiliary fields. And yeah, this is an instructive exercise to see how one structure transforms to another one. So we just checked how to go from just at the level of usual Lagrangian formalism, how to go from Hamiltonian action to usual second order action in these examples. I think we did the same for Maxwell. It's equally simple. Usually momenta is just an auxiliary field. But in fact, if we uplift all this to BFV formalism and its associated BV, you can do analogous elimination, but already of generalized auxiliary fields, leading to a usual BV for second order action. So this somehow shows us that we can rederive BV formulation starting from Hamiltonian. But Hamiltonian quantum mechanics is kind of first principle definition of what quantization should be, right? So we know that we can define operators, we can define quantum averages of operators, and then we can just, at a purely technical level, reformulate everything in terms of path integrals. And then we can go to Lagrangian formalism and derive BV formulation. Of course, this is going to be BV formulation for first order action, for Hamiltonian action, but then exactly as in this exercise, one can check that one can eliminate momenta together with their antifields to get to usual Lagrangian formulation. So this, of course, it's not a proof in mathematical sense, especially because once we are dealing with field theory, everything is quite subtle. But at formal level, it is a proof that we can derive BV from BFV, and usually it's considered as a proof of equivalence of BV formulation and BFV formulation. So, of course, there are many subtleties which are hidden in this discussion, because it's not a very simple step to relate Hamiltonian Lagrangian formalism for gauge theories. But one subtlety is instructive, and I'm going to discuss it in some details. So the point is that if ye, let's get back to this Hamiltonian gauge fixing. So we want this path integral of a Hamiltonian action. We want this path integral, and we treat K as a gauge fixing fermion because it fixes a complete Hamiltonian for us. Gauge fixing fermion. Fixing fermion. Okay. So what? If it's perfectly fine to work just like this if we are studying mechanical systems. But if we really want to treat field theory in this way, we will see that the gauges which we can access in this formulation are so-called unitary gauges, and they are not manifestly Lorentz invariant in field theory. Why? Because, for instance, take Maxwell theory. In Maxwell theory, what is omega? It's integral d3x, right, in 3-dimensional. Then we have constraints di pi times c, right? This is our constraint. And so we have Ghost c and Ghost p. And our constraint is not Lorentz invariant. And whatever we put here, we can't access, for instance, Lorentz gauge. Even our action, which we get, which is contained in this action, in this case, is not going to be a full-scale covariant Maxwell action, because it's not going to contain Lagrange multipliers, which are zero temporal components of our potential, right? Because again, in Maxwell theory, we have AI, we have PI, canonical coordinate momenta, A naught is a Lagrange multiplier. These are all our variables, and this is our constraint. So A naught is a Lagrange multiplier. It's not present in this section, right? Because it can only be its particular value of A naught can be implemented by choosing specific K. So we don't even have a room to impose Lorentz gauges. No room to impose d mu A mu equals 0. Suppose we want to quantize in Lorentz gauge. So what is the way out? The way out is again to equivalently reformulate our system. And the idea is to add non-minimal sector, so introduce new variables. Let me stress. So there is nothing wrong in this treatment. It's very basic, very fundamental. It's just not convenient technically because it doesn't allow us to work with explicitly covariant formulations because we don't have enough variables. But the logic is very simple. But there is a simple trick how to incorporate necessary variables to access covariant gauges. And the idea is to introduce new variables. They are like generalized auxiliary fields, but in Hamiltonian formalism. So they are like trivial. So these are new variables, non-minimal variables, which are lambda. Now we introduce Lagrange multipliers by hands. Their conjugate momenta pi. So this is, let's say, beta, delta, alpha, beta. And so-called anti-ghost variables, exactly like in Lagrangian formalism. To formulate gauge fixing, we had to introduce additional ghosts, because otherwise we were not able to write down gauge fixing fermion, because we simply were missing variables of degree -1. So here we do have variables of degree -1, which are ghost momenta, but these do not help us to access covariant gauges. So what we want another pair, which is C bar alpha and P bar alpha. And they are also canonically conjugated, and they are fermionic. So degree here is 0, 0, and degree here is -1, 1. And now we can write down non-minimal omega, which is an extension analogous to non-minimal extension of mass direction. So it's our initial omega plus just one moment, let me remember. Yeah, this one. So you see, this has a right degree because P bar has degree 1 and pi alpha has degree 0. So it has a right degree, and it's exactly analogous. It's algebraically identical to generalized auxiliary fields. In particular, they do not enter in cogomology. If we evaluate cogomology of Beresty differential determined by omega non-minimal, this is going to be isomorphic to Beresty cogomology determined by omega. Algebraically, it's identical. Exercise check. Let's check that H of S non-minimal is isomorphic to H of S, where the differential is just a Hamiltonian vector field generated by respective omega. But now, with these additional variables, we have Lagrange multipliers, which are temporal components in the example of Maxwell. These are temporal components of our gauge field. So we have enough variables to have covariant gauges. And for instance, we can consider gauge fixing fermion of the following type: C bar chi minus pi alpha lambda alpha, where chi are gauge conditions, and C bar, pi lambda our variables. And now we can compute H plus omega k. The new terms in our action are going to be here, right? So let's just compute this. So what we are going to have is H plus, so which contribution do we get here? So first of all, and let me remind you that omega looks like this: C alpha T alpha plus more. And we only keep the leading contributions because only them are important. So what do we get? We get the following term: C alpha T alpha I beta C bar beta, right? This is the first one. This comes from here. Then we get so the C bar, another contribution, C bar is conjugated to P bar, which is present in non-minimal omega, and it gives us lambda alpha chi alpha contribution. And then the additional contribution is oh, sorry. Pi alpha here, sorry, I'm not correct. Pi alpha, and then the additional contribution comes from here, from the second term, and this is, you see, when P alpha hits C alpha, we get standard lambda alpha T alpha term, right? And actually, yeah, and that's it. So these are our new terms. Now look at them more carefully. So this is our initial Hamiltonian. This is the term which is, in fact, the Hamiltonian version of Fadeev-Popov term, because it takes care when we integrate over C and C bar, we get a determinant of this matrix, which gives us a right measure on the integration measure on the surface. This term implements, oh, no, here is a mistake. Sorry. Here is a mistake. So which term is here? Here is the following. You see, you have this C bar, you have C bar here, which is going to give a delta symbol in a Poisson bracket with pi bar present in non-minimal omega. So what we get is chi alpha, pi alpha. Pi alpha are so chi alpha are gauge conditions, and pi alpha are variables of degree 0. So this is precisely the term. So if you integrate over pi, we get a delta function of chi, which is our gauge. And this is a standard term in the action, which, remember, in the Hamiltonian action, we should have a term lambda alpha T alpha. So in fact, what we got with this Hamiltonian prescription, it's like a Hamiltonian version. A Hamiltonian version of Fadeev-Popov. And in fact, an exercise, good exercise, already bit more involved than the ones before. Take Maxwell, and show that this gives usual Fadeev-Popov by elimination of momenta. And in this way, we already can incorporate, for instance, Lorentz gauge as these conditions lambda, because now we have all variables. We have Lagrange multipliers, we have lambdas, which in case of Maxwell are temporal components of our gauge field. Then we have spatial components of our gauge field. These are phase space variables, and we have momenta. So we have enough of variables to write down, for instance, Lorentz gauge. So you can pick chi to be a Lorentz gauge condition, do this prescription explicitly for Maxwell, get certain gauge fixed action of Fadeev-Popov type, and then eliminate momenta to get the usual Fadeev-Popov action, which we discussed last time. It's a good exercise to see how Hamiltonian path integral transforms in a gauge fixed version to the Lagrangian path integral. I'm afraid time is over.